Hello everyone, I presented my work on INR, a novel regularizer that improves the generalization ability of INR. INR uses Dirichlet energy to measure similarities between rows columns of the matrix, integrating the smoothness of the Laplacian matrix. INR represents various signals by mapping coordinates to signal values, as shown in the top row of slides. INR can be used to represent sound, images, 3D scenes, and objects. However, the initial use of ReLU as the activation function did not represent high-frequency signals well. Therefore, in NeurIPS 2020, researchers proposed using Fourier features to map input coordinates to obtain better representation performance for high-frequency signals. Similarly, the work Siren, also published in NeurIPS 2020, directly replaced the ReLU activation function with the sine function and achieved better results than simply mapping input coordinates. This is shown in the second row of the slides. Furthermore, the work published at CVPR 2022 restricted the weights of each sine function in each layer to control the frequency band of signal representation. However, these works have focused on the representational power of the signals. Our research has found that although these improvements greatly improve the representational power of the signals, the improvement in generalization performance is limited, and the generalization performance of the signals is precisely what we are more concerned about in the practical application process. In this paper, we used the neural tangent kernel, NTK, as a theoretical tool to analyze the generalization performance of INR with feature maps and the relationship between the hyperparameter delta of the feature map. We found that INR primarily weights the input data during prediction, and the range of data used depends on the size of delta. A small delta results in training points far from the test point having more weight, resulting in a smoother overall prediction. The experiments below also support our idea. Based on previous theoretical analyses and experimental results, different missing rates correspond to different optimal hyperparameters delta. However, when using INR to characterize non-uniform missing data, it is difficult to select a delta that generalizes well globally. Therefore, we propose adding an additional tiny INR to regularize the original INR, which we call INRR. INRR can capture the non-local self-similarity in the signal, and then use this self-similarity to further improve the generalization ability of the original INR. We propose that the INRR is effective for characterizing signals other than the INR. Therefore, here we use X to represent the characterized signal, which may be a signal characterized by the INR or other parameterization methods. Let's focus on the proposed regularizer INRR. First, we introduce the Dirichlet energy, D, which is a regularization term that can be used to describe the similarity between rows of X, that is, based on D, we can utilize the non-local similarity in the signal. However, A is usually unknown in the task, so we propose a parameterization method to make the originally fixed regularization term learnable. Our proposed parameterization method preserves the two properties of A. First, all elements age of A are greater than or equal to 0. Second, A is a symmetric matrix. Our parameterization scheme is given at the bottom, and it can be verified that our parameterization scheme enables A to maintain its existing properties. With such a parameterized regularization term, we can add the regularization term R theta to the original loss function and optimize it together with the original parameters. These are some of our experimental results. Our tasks are all based on incomplete image tasks. First, we show that INRR can improve performance on different data representations. The results with a plus sign represent the results of additional regularization using INRR. DMF stands for Deep Matrix Factorization, and ReLU, Siren, Garba, and Fourier are all INRs, but with slightly different architectures and activation functions. We found that different structures benefited from INRR regularization. In particular, for structures like DMF that are prone to overfitting, our method achieved the largest improvement in performance. Additionally, we visually demonstrated the effectiveness of our method. The figure shows the residual between the reconstructed images using different methods and the ground truth images. The last column shows our results, which significantly improved the performance of the images when used with non-uniform missing data. Next, I will present some interesting properties of INRR. First, INRR is learnable, and we drew the learned Laplacian matrices. Different columns represent Laplacian matrices learned at different training epochs. The first row represents the similarity between rows of the learned matrix, and the second row represents the similarity between columns of the learned matrix. In particular, let us focus on the second row, where the similarity between the two eyes of the baboon image is captured by our proposed learnable regularization. Moreover, at t equals 500, the captured similarity has a relatively large scale, and as the training progresses, the similarity gradually focuses on a smaller scale. Finally, the disappearing similarity also avoids INR from overregularizing INR. The second interesting property of INRR is that it gives INR a momentum-like behavior during convergence. Our experiments involve completing images with different missing values. The figure below shows the evolution of the image restoration process using vanilla INR, TV regularization, L2 regularization, air regularization, the discrete version of our method, and INR regularization, respectively. The horizontal axis represents the MSE of the recovered image on the observed pixels, and the vertical axis represents the MSE of the recovered image on the unobserved pixels. The small circle in the upper right corner of the figure represents the MSE state at initialization for each method. The diamond in the lower left corner represents the MSE state when the observation value drops to a specific value. It can be seen that the unobserved MSE of vanilla INR and TVL2 first decreases, and then increases as the observed MSE decreases. However, air and INR always maintain this downward trend, which is very similar to the effect brought by the momentum method in optimization algorithms. In particular, due to the use of data smoothness, INR performs slightly better than air. Finally, we would like to discuss the extensibility of INRR. Though our experiments were focused on image completion, our method can be easily extended to other tasks and higher-dimensional data. We also demonstrate the effectiveness of INRR in learning noisy data, achieving superior results compared to vanilla methods. In addition, we apply INRR to video data and observe that it captures similarities between frames. That concludes our presentation on the content of this year's CVPR. For more detailed information, please refer to the original paper. Thank you again for your attention.